Yep, so it's working this time, so I have no idea why it didn't work before. All right, so let me check the audio settings. It's using the correct mic. I can now share screen. Stop 2. There we go. And it should be recording by itself already. Yep. Cool. All right, so we got everything that we need. All right, so first question is, do you want me to go over the homework assignment? Yes. Okay, let's go ahead and do that. Some people told me that it timed out on certain people. So I try my best to kind of keep up with those email messages and give people a second attempt if it timed out on people. I have no idea why, because resetting the due date should not have done anything along that line. And it's not, I did not change the due date by 1 day either. So that's really kind of strange. All right, so we'll go to function assignment and go ahead and do all the questions. All right, so all the questions or most of the questions are in this particular format. You want to basically add up the following numbers. 1, if and only if f is a function to begin with. 2 is if and only if f is a function and it is also injective, because injection does not make any sense unless we are talking about a function to begin with. And then to add a 4, if and only if f is a function and it is also surjective. So at the most, if you get a bijection, you can add up to 7. And if you have something that is not even a function to begin with, you can end up with a 0, which Canvas will annoyingly say you did not answer the question, because it would mistake an answer of 0 as not answering. It's a very common scripting error or mistake to make. And I even made a suggestion to Canvas of where the bug might be, and suggest them to fix the bug. And so far they have not fixed it. They have not done anything with it for 5 years. Yep. So this is why I like open source stuff, because I can just go ahead and fix it myself and not having to worry about it. All right, so let's go take a look at this particular question. This is not even a function, because the domain, how do we know this is the domain? Because it is supposed to be going from the domain X to the codomain Y. But we can see the element 1 from the domain is not mapping to anything in the codomain. And as a result, it is not even a function. So that makes it kind of easy, because it's going to have a number of 0.
Can you also say it's not 1 to 1?
Huh?
Can you say it's not 1 to 1?
Can you say it's not
answer
in the exam? It's not a function. So I'm not sure if the question is phrased exactly like this, then you have the answer with a 0. Because it is not even a function. If it's not a function, then it cannot be injective or surjective. Okay. Yep.
And also, if we have we have 1 input output to 2 outputs. Is that another reason that it's not?
Yep, that is the other reason. So there are multiple reasons why this is not a function, because the element 2 from the domain is mapping to 0 and also 2. So that means the cardinality of the set, or the number of things that an element maps to. 1 maps to nothing, so that's a 0, which is not 1. And then 2 maps to 2 things, which is also not 1, because we want that cardinality to be exactly 1. Yep.
Say I want to configure a function in relation to the 0 and the domain.
Say that one more time.
So the first reason you stated is was.
Yes, it is not a function to begin with, so that's why we don't even have to evaluate the rest. So what is your question?
Oh, I see.
Yeah, because the other 2 numbers is saying if and only if f is a function and blah blah blah. So if it is not a function to begin with, this entire condition is false, which means we're not going to add 2 or 4 to this sum. All right. Any other questions before we move on to number 2? Okay, so we're moving on to number 2. All right. So this one is, okay, so we got 0, 1, 2 in the domain, and then we also got 0, 1, 2 in the mapping. So it is at least a function. So we have at least a 1. Now the next question is it injective? It is not injective because 0 maps to 2, 2 also maps to 2. So it is not injective. The third question is it surjective? It cannot possibly be surjective because the codomain has more elements than the domain. So that pretty much answers all the questions. So in this case, it is just a 1 because yes, it is a function, but it is not injective and it is also not surjective. Moving on to the next one. All right, so this one is a function because I can see 0, 1, and 2 are in the domain and 0, 1, 2 are all mapped to certain things in the codomain. But once again, it is not injective because 1 and 2 both map to 0. So it is not injective. It is also not surjective because the element 2 in the codomain is not mapped to. So once again, we only got a 1 here. And moving along, same kind of question. And this is a function. It is also just a 1 because it is a function, but it is not injective. It is not injective because 0 maps to 0, 1 also maps to 0. It is not surjective because 2 in the codomain is not mapped to 2. Moving along, number 5. Okay, so this is a function. I think it's the same thing as the previous one. So occasionally it does repeat the questions because there are only so many cases for each one that you can pull from. All right, so with this one, it is a function and it is also neither injection or surjection. So it is also just a 1. And then here's the last one, I think. With this one, it is not a function, so we put a 0 here. Yep.
I'm pretty sure I ran into a question where it repeated the function. So it was like, let's see if I can find it. It had like 2, 0, and then again 2, 0. Yeah. And I got that wrong. So
Yeah, so my initial rationalization was that it was a function because it should just reduce to a set with the 2 elements in it that are different. But then, now that I'm thinking about it, because it had 3 elements and 2 of them were duplicates, and there was 3 elements in the code, in the domain and the codomain, that means that not all 3 elements in the domain were accounted for, and so therefore it is not a function.
Right. Okay. Exactly. So there, yeah, go ahead.
So let's show you.
Probably won't be talking about this unless it is a. So this is a function. This is not a function.
Didn't I answer not a function? No, I just,
It is definitely not a function because it's not even a set.
Okay, so
So in his case, there are 2 tuples that are identical in the set.
does that not reduce then because?
Yeah, but even if you reduce, it is still not a function because the statement here states that we want X to be the domain.
Right.
So if one thing is missing, we're definitely not having a function. So this is also a 0 in this case. Semi-quiz. And all right, so I think I got 1 out of 1. Okay, just look for the color, right? So they're all correct. There we go. All right, so are there any questions about the assignment? Any questions about what makes a function surjective or what makes a function injective? Yep.
So if on the text you gave us a function that was a set with duplicate elements, but even after reduction, all of the x's were accounted for, would that be considered a function then?
If there's a duplicate, if there's an element of the domain mapping to 2 different elements in the codomain, it would still not be a function.
Right, but if it's an element in the domain mapping to the same element in the codomain, just 2 times. So if it went like 1, 1, 1, 1,
Okay,
et cetera, et cetera.
In that case, you probably want to ask me. Because I don't think the exam should include, errors like that. Yep, but you probably want to ask me. Because the script that I use to generate questions for the exam has the concept of a set, whereas in this one does not. I have to jump through a lot of hoops in Canvas to ask questions like these, where there's some randomization and there's some calculation involved. So it's just kind of different. The exam is using an entirely different mechanism to generate. All right, any other questions? Yep.
So in the case that elements are in the set.
It is not a set to begin with. Yeah. All righty. Okay, so let me go back to the modules if there are no questions about this. So we're going to continue the discussion of relations at this point. And since it has been a week since the last time we talked about relations, do you guys retain what we talked about last time? Well, I like the honesty for sure. Okay, I like the honesty that people are just going like, it's been a week. All right, so we'll go ahead and kind of quickly recap, what a relation is, and then we'll move forward to talk about properties of a relation. So a relation, okay, let me zoom in just a little bit here. So in order to define a relation over a particular set, so in this case, we're defining a relation R over a set X here. So the only requirement is for R to be a subset of the Cartesian product of X with itself. That's the only requirement, okay, in order for R as a set to be considered a relation. That's it, okay? So that means, we can have, interesting examples. So let me go ahead and use Joplin to capture some of the examples. So I'm going to move Joplin into the window being recorded. And also go back to 440, make a new note for today. And today is 2023, February 22nd. There we go. And then now at this point, we can get rid of the other two windows. All right, so we'll go ahead and define what X is first, okay, because that is important. So let's just say the X has 3 elements, 0, 1, and 2. And I need to use backslash here just so that it shows up as an equation correctly, like so. So that means R can be anything that is a subset. Okay, so R has to be a subset EQ of the Cartesian product. So in this case, the Cartesian product is not too bad. I can just enumerate everything. So we got 0, 0, 0, 1, oops, 0, 2, 1, 0, 1, 1, 1, 2, and then we have 2, 0, 2, 1, and 2, 2. So are we doing okay so far with the first requirement of a relation? It has to be a subset of the Cartesian product of whatever set it is defined over with itself. Is that okay? All right. So that means we have a lot of possibilities for R in this case. So in this case, R being the, okay, let me go back to use the math notation here. This is a relation. It's an empty relation, but nonetheless, it is a relation because is the empty set a subset of this big set over here? Yep, not a problem, okay? So another possibility is, oh, it is really just the Cartesian product. Okay, you can have this can be a relation. The entire Cartesian product is a relation because it is also its own subset. Is that okay? So basically, there's no real restriction. Just like in the case of function, there's a pile of restrictions. Okay, in the case of relation, yeah, as long as it is a subset of the Cartesian product, it's all good. So are we good so far in terms of the only restriction of a relation? Okay. So then we also talked about using the beer commercial of, why relations are useful, because we need, in many cases, things to be totally ordered. So if you want to sort something, okay, you need a relation that is totally ordered. So in that case, what we call a relation is really just a comparison operator or a relational operator, as it is called in C++. But we need it to be totally ordered, which means if you pick any two values out of X, I can tell you whether these two things relate in this way or in the opposite way. Okay, if I can pick out two things in the set X and they do not relate to each other in any way, then we have a problem. Okay, because in that case, how do you sort when you cannot truly compare the value between any two elements within the set of values that can be presented in the array? Is that making any sense? So this is the main reason why we have to understand relations. Okay, so that's a quick recap of what we have talked about so far. And then what we'll do now is we're going to move ahead and continue to talk about properties of relations. So I'm just going to move ahead here until we get to section 5. So section 5 makes use of quantified expressions to state what does it mean when we have a relation that is reflexive, symmetric, transitive, asymmetric, antisymmetric, and also transitive. So we'll start with the easy one. The easy one is being reflexive. So being reflexive means, as the equation says right here, it says for all element E in X, the two tuple EE has to be an element of R. If that condition is satisfied, then the relation R defined over X is said to be reflexive. I should say if and only if. I said if, but it really should have been if and only if this quantified expression is true, then the relation is called reflexive. All right, so let's go through a few examples so that you guys can tell me whether something is reflexive or not. So are we good so far? All right. I am going to also copy the equation itself. So this way in Joplin, it will also show up. So this way you can kind of relate the definition with the interpretation in Joplin. So I'm just gonna copy and paste this into Joplin. Okay. One of the many reasons why I like Joplin. One is I can do this. Okay, so now I can give you some examples. So we'll say, what about this R? So assuming X is 0, 1, 2, so we are maintaining X to be like this. So we are just changing the definition of R, and you're going to tell me whether that R is reflexive or not. So we'll start with something that's simple. What if R is empty? Is R reflexive over X? It is not, because it's missing the three things that we need. Okay, so it is not reflexive. So we'll say is not reflexive, given that we are trying to define R over X. X as defined up here. All right, let's move on to another example then. So what if R has 1, 1? Oh, okay, go ahead. You first and then you. Go ahead.
So it's not reflective. So if the set is 0, 1, 2, it's not reflexive.
If R is defined to be the empty set, it is not reflexive. Because there are two things. One is R, which is the relation, but we also have to understand what set it is defined over. And in this case, it's defined over X, which has the elements 0, 1, 2. So we should be expecting 0, 0, 1, 1, and 2, 2 in R in order for R to be reflexive. Okay, go ahead.
And then the empty set is a relation for all types of sets, or is
Well, the empty set is a possible relation,
that's not?
but it is not reflexive in this case. Okay, I can give you an example when the empty relation is actually reflexive. So think about that a little bit. Go ahead.
Things are reflexive
Well, R can never be a subset of X. Because R is supposed to be a subset of the Cartesian product of X with itself. The requirement, the restriction is R has to be a subset of the Cartesian product of X with itself. So R can not really be a subset of X itself. Well, okay, I take it back, because if R is the empty set, then yes, it is a subset of every set there is to exist, but in general, it is not true. Yep.
So if that R was defined as anything, but I had those elements in it, then it would be. So if R was 0, 0, 1, 1, 2, 2, specifically.
So let's get through this one first, and then we'll get to that one. Okay. So this one is not reflexive because 0, 0 is missing, 2, 2 is also missing. So in your case, okay, in your example, you're saying, okay, what if we give it everything that it needs, right? What if it has 0, 0, 1, 1, and 2, 2 in it? Then the answer is this is indeed reflexive.
And what if you have all those and 1 more? Is it not reflexive anymore?
Well, okay, that's a very good question, but I think you should be able to figure out the answer as well. So we'll go ahead and take a look at that, okay? So we'll have 0, 0, 1, 1, 2, 2, and we'll add one more, okay? We'll add 0, 2, okay? Yeah, just like that. So the question is this reflexive or not? The latest example here, is it reflexive? Based on the definition of whether a relation is reflexive. Well, let's take a look at the definition again, okay? For every E in X, so that means 0, 1, and 2. So imagine this is a loop, and the loop is going through all the elements of X, okay? The first iteration, E equals to 0. The second iteration, E equals to 1. And then the third and last iteration, E equals to 2. Is that okay? So I know I'm asking you to imagine the running of a loop, but I think you got the idea, right? Okay. So then we ask, when E is 0, is E 0, 0 in R? Yep, right there. And then when E equals to 1, is 1, 1 in R? Yep, got it. And then we ask, when E is 2, is 2, 2 in R? Yep, got that too. So whatever you have extra in R does not matter in this case, because we only need to confirm the existence of 0, 0, 1, 1, 2, 2 in this specific example. If you have some extra stuff in R, hey, it does not interfere with the qualification of being reflexive. Is that okay? Yep.
It does not matter where that 0, 2 is on the set, it could be in the front too.
Yeah, because if it's a set, then the ordering is not important. So there's no intrinsic ordering of elements within a set to begin with. All right, yep.
In order to be reflexive, do they have to be mapped with their own selves? Like 0, 0, can you have 0, 1, 1, 2, and 2, 0? Is that reflexive?
You have to go back to this definition here. So according to the, okay, so one thing I want you guys to do is to change this notation into C++ code. Okay, based on what you have learned already, because all of you have taken CISP440 already. So I'm imagining that you already understand how to make a loop, how to iterate through an array, and so on. Okay, so basically this is a loop, and I'm pretty sure I presented the pseudocode already for the for all and there exist. So that's what you need to do, is to go back to that definition, mapping the notation, the math notation, to actual procedural logic. And then you plug in, okay, in this case, you plug in the condition here into that loop that I have mentioned already. And also you'll plug in X being a set of 0, 1, 2, and R being a set with 0, 0, 1, 1, 2, 2, and 0, 2. And then see what kind of answer you come back with. Because that's a concrete way to look at this, because otherwise, these concepts can be a little bit abstract, but once you translate that into actual concrete code that you understand, then you grasp the idea. Is that okay so far? Because from what I'm hearing, there seem to be some questions regarding how do we use the for all universal quantifier. Is that right or not? Okay. So if that is the case, okay, you're assuming that is the case for some people, then you have to go back to a previous lecture where I gave you guys the code that represents what for all is actually trying to do. Yes, this is a very infamous thing that I do in all of my classes is, yep, pretty sure we talked about it. It is your job to go back and figure out where, when I talk about it and locate that note. All right. If you absolutely cannot find it, I will help you, but not during class. You can do it during office hours. All right, so let's go take a look at another example, okay? Because I think this one should not be that confusing. So we'll have 0, 1, 1, 0, 2, 2, and 0, 0. Okay, so is that reflexive? It is not reflexive. This is not reflexive because, hey, where's 0, 0? 0, 0 is here. 1, 1 is missing. So this one is reflexive as well, but this one is not. Are we doing okay with what makes something reflexive? Okay. But I do understand that some people may have a more fundamental question of what does for all mean? Because that seems to be one of the obstacles that I hear earlier. So that means for those people, it is important to go back to an earlier point of this class and clarify what does it mean when we use the for all quantifier. All right. So now the next question is, what else can we use to describe a relation other than being reflexive? So the next one is symmetric. So we'll go ahead and do the same thing. Okay, I'm just going to copy the LaTeX representation, switch back to Joplin, and then just kind of paste that in. So this way we can reference the definition as we go through examples. All right, so before we do that, before we go through some examples, let me just emphasize that this symbol here is really, really important in this case. So the first question is, what is it? What is the double-sided arrow thing that has 2 bars? Equivalence, if and only if, the same, okay? So those are all slightly different but valid way to describe the double-sided equal thing. How is it defined? Well, there's a truth table that defines what is equivalent to. So where do we find that truth table? The first module, okay? The very, very first module that we talked about in this class, like way back in week 1, is when we looked at that truth table. But the thing is, this is an operator. This is a Boolean operator. The value of the expressions depends on what is on the left-hand side and what is on the right-hand side. Okay, so let's go ahead and take a look at a few examples. So we'll go ahead, me being super lazy is going to recycle some of the examples. So we'll use the empty relation first and ask, is the empty relation symmetric?
Yes, it is.
The answer is yes, it is, okay? Because you still have to use a double loop in this case, okay? So the reason why you have to use a double loop is the outer loop is going to iterate through, every single way to give E of a value. So E is going to go through 0, 1, 2. The inner loop is going to iterate through all the possible values for F. So F can also be 0, 1, 2. So you're basically looking at all the possible ways to pair up your 0, 1, 2 as variables E and F. Is that okay? And some of you are gonna say, well, but what does it matter? Because the set itself is empty. You are absolutely right. So that means this side has to be false. E, F in R has to be false because R is empty. There's nothing in it. Is that okay? But when you look at the right-hand side of the if and only if, it's the same situation. It is empty. FE cannot possibly be in R. So now, regardless of the value of E and F, you end up with false if and only if false. I will defer you to look up the truth table to understand why false if and only if false is true. Yes.
But it's always true if the first part of the implication is false, right? So you don't need to do the second.
But this is not the implication. This is the if and only if. If the arrow is only going in one direction, it is a if, but if it's going in both directions, it is if and only if. So it's important to make that difference because later on we'll see if, okay? Some of the definitions rely on if, okay? So once again, this is building upon things that we have talked about already. So the mastery of operators is really important at this point. Yep.
Could we view that quantified statement, which says for EF and you said for EF as a tuple in X, continue from X and X.
I'm not exactly sure what you're saying.
So to consider all the elements in X, X is the continuum of X and X. Wouldn't that be the same thing as you said for EF and X? Combination.
Yeah, you could do it this way in this case. So let me clarify, make sure that I understand what you're saying correctly. So what you're suggesting is to change the notation. So you have basically for all, and then you use EF here in X times X. And then the rest being the same. Right? Yeah, I mean, the rest being this ... stuff. So the answer is yes, you can do it that way too, because you're still iterating through all the possible ways of pairing up, two variables with each other. Yep, so that would be the same. Yep. But it takes more typing. I mean, there's another way to put it too. I mean, if you want to look at alternatives, and this is what I said a little bit earlier, is to look at different ways of expressing the same thing, that trains your brain to be more flexible. It's like, no, this is not the only way to say this. So I really like, how what you're doing here is to say, but isn't that the same thing as, this way here? Yep, it is, but there's another way. So what you can do is to say for all E in X, and then, put it in another construct. And then now you say for all F in X, and now you say the blah, blah, blah. So that would still be the same, except in this case, you're basically just making it very explicit that we have two loops. One loop to iterate through all the possible things for E, another one to iterate all the possible things for F. And then whatever we specify here, the ... which is basically this portion here, goes into both all of those. And these three expressions would be basically saying the same thing. But I like the first one because it is a little bit more concise. So we good so far? Okay. So, alternative expressions and the value of talking about the alternative ways to expressing the same thing is it is also a good way to check your understanding of the concepts. Because if you look at these alternative expressions and go like, yep, I can see how they're equivalent. That's a good thing. If you say, I cannot see how they're the same thing, that means you might need to spend some more time to understand, how the for all quantifier works. So, that's a very good exercise to go through. All right. So, question? No. Okay. So now we'll try another one, because I'm lazy. So I'm just going to recycle some of the earlier examples, and before we do that, we have to say this one is indeed symmetric. So the question now is, how about this one? We know it's a reflexive, right? But at this point, I'm only focusing on whether it is symmetric or not. So I'm not going to say whether it is reflexive or not. I just want to know, is it also symmetric? What do you think?
Yes.
Yep, it's definitely reflexive. Okay. So symmetric side. So this is also symmetric. Very good. And now we take a look at another example. Oh, I know. I'll be consistently lazy. What about this one? Is it symmetric? I know it's reflexive because we said so earlier, but is it symmetric? You have to go back to the definition. Okay, so go back and look at the definition and you ask, is there a way that I can take the values E and F such that E is an element of X, F is an element of X, but somehow this expression using the if and only if is false. One side is true, the other one is false. What if I make, yeah, go ahead.
What is the function?
Hmm?
What is the function?
F in this case is not a function, it is merely a variable representing an element of X.
Is it just like, so it's just another.
Well, E is the placeholder for an element of X, and F is another variable to hold an element of X. So the question is there a way for me to find a value for E and a value for F, such that E and F are both elements of X, and yet this if and only if turns out to be false? Yes. E to be 0 and F to be 2, yep, that will do the trick, right? Because if I pick E to be 0 and F to be 2, then EF in R is true because we got 0, 2 here, but FE, which is 2, 0 in R, would have been false. So now we have true if and only if false. And when you look up the truth table, it will tell you true if and only if false is false, because the two sides are not the same. Is that okay? All right. Yep.
I'm just sorry to be confused. Do you have to, you don't have to do that for every, possible value in X, right?
I'm not sure to what you're referring.
So if you had like a 0, 2, and then you had a 2, 0,
Mhm.
that would, yeah, that would be symmetric.
That would have been symmetric, yes.
So you don't have to do that for every possible, value of,
Okay, so let me see if I can capture your question. So I'm gonna use this example or reuse that example. And I'm gonna ask, is that symmetric? This one here, the last R, is that symmetric? We know it's not reflexive because it's missing 1, 1, but is it symmetric? The answer is yes, it is symmetric. Because no matter which way you assign values to E and F, the if and only if is always true.
and in order to be symmetric, it has to be true for every element in the set.
To be more precise, the if and only if expression has to be true regardless of what you choose as E and what you choose as F, as long as they are both elements of X.
I think what's being is just like in the 1, 1 set.
The 1, 1 set.
Yeah. 2, that's the one after the empty set.
Oh,
That doesn't include 2 and 0, which are in X.
okay, so let's try this one. Okay, but before we do that, let me answer this question first. This one is indeed symmetric. So the question is, what about this one here? What if, R is just 1, 1? Is it symmetric? It is symmetric. Yep. All right, very good. Oops, I keep, doing, this page pops up because I, attempt to save the file and I didn't pay for the subscription. So, it's asking me, hey, do you want to pay? I can host your content in the cloud. Yep. It is not that 0, 0 itself is symmetric. It is the set containing 0, 1, 1, 0, 2, 2, 0, 0 is a symmetric relation defined over X. Because it meets the requirement, because the requirement is this part here. It meets this requirement. This statement is true when R is like this. Yep.
So the empty set makes the equivalence false on both sides, right?
Yes.
Is that the only set that does that, the empty set, or is there other sets as well? So the last one would.
Well, the last one is not gonna, it's not gonna be false for everything, because when E equals to 1 and F equals to 1, then we have true if and only if true, but also true.
For other elements of X.
For anything other than 1.
Yes.
If E and F are anything other than 1, then we would have if and only if still being true, but because both sides are false in those cases.
So just anything that's, I see, okay, thank you.
All right. Any other questions?
Like the easiest, one of the easiest examples is like R equals 0, 1, comma 1, 0.
Or the empty set. The empty set is really the easiest. It's the simplest relation that is symmetric, but it doesn't illustrate what it means to be symmetric. All right, is that okay? I don't see any questions. All right. All right, so I'll give you guys a short break by taking roll at this point. Yes, I'm gonna have to take roll. And then I have not set up anything yet, so this will take me a little bit of time. I'm gonna reuse this one. All right, so today is February 22nd. And we'll set up, someone just left classroom right at this point. All right. All right, so we'll use reflexive. There we go. So reflexive is the passcode. And I have to adjust the question too. So I have to give you guys, I'll give you until like 1 p.m.
Do we still have the barcode?
No, don't have the barcode. So you're gonna have to scan the whole thing. Just refresh when I tell you to. Not yet. All right, so go ahead and change this to I am in class today. It's going to be a true false question. So Canvas is really kind of lame because I have to update the question first, then I save and publish, because otherwise it is not going to update the question, even though if I release the quiz. So here we go. You should be able to refresh and see roll taking 2023-02-22. And I'm just going to write this on the board. Reflexive for roll taking. So when that person comes back, I hope this will help. Unless that person comes back after 1 p.m. All right, so do that stuff, and I'm going to go back to the notes and get ready for the next one. transitive is not really difficult, even though it has an implication. But I'm gonna just pause here until yes, both of them come back. At least, he took row first before he left the classroom. The other person left the classroom knowing that I was about to take row. But sometimes when you have to go, you have to go. Great. So for the rest of us, I think most of you are done. Does anyone need more time? No? Okay. So we're going to look at transitive. So transitive is a little bit, it looks a little bit more complex, but it's not really that much bad, that much worse than the other one. So now we have three variables. E, F, G are all elements of X, okay? And then we basically say, what do we want to be true? Doesn't, regardless of how I put values into E, F, G, as long as they are elements of X. I want EF to be in R and FG to be in R, but that, the conjunction here is used to imply EG is in R. So this is the time when we are switching from if and only if or simply existing to something that's a little bit more interesting, which is the implication. So let me go ahead and do the same trick here and just right click, copy the text representation, and then we'll put it into Joplin so that we can go through a few examples, just like with the other ones. Okay, there we go. And I'm going to go through the same examples. So 1, 2, 3, 4, 5. So there are 5 of these. And with this one, I'm going to need some extra examples too. So we'll go ahead and get to those extra examples when we get to them. Okay. All right, so the first one is always the empty set. So the question is the empty set transitive? Okay. So this time you really kind of have to remember what implication means. Well, and also what conjunction means, because the left-hand side of the implication is a conjunction. And then each element or each side of the conjunction is element of. So because R is empty, this is what we're considering right now. So that means the element of has to come back with an answer of false. There's nothing in R, right? So if it is false and false, then it is false. Okay, false and false is false. So that means the left-hand side of the implication is false. Yep, exactly. So the implication is guaranteed to be true. So that means, the entire thing, this relation R being the empty set is transitive. Is that okay? Does everybody understand why it is transitive? Or the quick way to understand why it's transitive? Now, the slow way of doing this is really setting up a triple loop. The outermost loop is going to iterate E through all the possible values. So E equals to 0, E equals 1, E equals 2. For each value of E, the medium inner loop is going to go through all the values for F. So while E equals to 0, F equals to 0, F equals 1, F equals 2. And then you have to set up an innermost loop for G, which is doing the same thing. G equals 0, G equals 1, G equals 2. This thing here is evaluated in the innermost part of the entire loop structure. And you just have to say, well, does this always give me an answer of true? Okay, so that is the procedural way to make sure that a particular relation is indeed transitive. But in this case, we can shortcut the entire thing. We can shortcut because we are saying element of got to be false. And if one side of conjunction is false, the entire conjunction is false. If the left-hand side of implication is false, the implication is true. So that means the implication has to be true all the time. Yep.
False if true. Is it like looking at it as a whole? False if true.
False implies true is true.
That's the.
Because the implication is an operator, even though it does not sound like an operator. Okay, so we took row earlier, and the word of row taking is reflexive. Okay. All right, so we got the first one done. We move on to the second one. Okay, what about this one here? Is it transitive or not? So this time, so if you say it's not transitive, then you have to give me an example of what does it take for this implication to be false. Okay, if you cannot find an example, then it's the implication is always true. So you have to kind of come up with a counterexample. For what values of E, F, and G can I make this implication false? Or is it not possible? Okay, if it's not possible, you can say, oh, okay, it's not possible. So that means it is indeed transitive. So what do you guys think? It is transitive. Okay, so this one is transitive. Okay. What about this one here? This one is a little bit interesting because we can handle the 0, 0, 1, 1, 2, 2 thing. What about this 0, 2 thing here? By introducing 0, 2, am I making something that would make this not transitive? So if you think it is making it not transitive, then you have to come up with an example where the implication is false. But it's easy to think about what can make an implication false, because you will need the left-hand side to be true and then the right-hand side to be false. So the question is, can I come up with a case like that? Can I come up with a case of E, F, and G so that E, F is in R and F, G is in R is true, but E, G is in R is false?
Zero, 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 two, and 2, 2.
0, 0,
And then 0, 2,
0, 2, okay.
2, 2.
But it won't be 2, 2 because it is 0, 2.
Oh.
Yep.
But that sign needs to be false, so.
You want this to be false and this side to be true.
I need just one. No, one.
Because if you want to make this one 1, 1, then you have to find the F as a bridge. Yep.
0, 0, 1, 1.
Okay, so instead of telling me the two tuples, what do you want to be in E, F, and G? E equals to 0. Okay, so we have 0 something. What about F? 1. Okay, 0, 1 is in R. Is handling this one is false to begin with. So this conjunction is going to be false. The left-hand side of the implication is false. The implication is going to be true. Yep.
So I guess the way to look at it is that we need EG to be false. So
We need EG in R to be false.
So we
Yep.
pick up two values like a 0, 2, and we just have to make sure part of the set R.
But
And
okay, go ahead.
G. We can have values like E, F, G. We can have it be 0, 2, and then have F be, I don't know, 1. So 0, 1.
0, 1 is not an element in R. Oh, okay, but let's focus on this particular definition of R because we want to focus on one example at a time.
So
Yep, go ahead.
E would be 0,
E means 0,
and then F would be 2.
F means 2,
So
okay.
it's 0, 2, and then 2, 2, and then G would be 2.
G would be 2.
And
So
then-
let's see what happens.
Oh, that's
0, 2 is in R. Yep. 2, 2 is in R. Yep. 0, 2 is in R. Yep. So this one is actually, go ahead.
So E is 0,
Mhm.
F is 1, G is 2.
Okay,
But
so
there's-
as soon as I hear E is 0, F is 1, I already know the answer is going to be, it's not going to work. It's not going to work as a counter example because EF in R means 0, 1 is in R, right? But 0, 1 is not in R in this case. As a result, the conjunction is false. And if the conjunction is false, then the left-hand side of the implication is false, which means the implication is true.
So that R is transitive.
Yep, that R is transitive. Yep.
Usually work this hard to find if it's transitive or not.
Well, you have to get used to it. You have to get used to what you're looking for. Okay, so this one, I'm going to give you the, go ahead. Oh, I thought you had a question.
Sorry.
Okay, so I'm going to tell you what this one is, and then you guys have to tell me why it is.
Oh, and then
Okay, go ahead.
1, 0, 0, 1, and then 1, 1.
Okay, so what do you want to be in E, F, and G respectively?
Okay, E is 1,
E is 1,
F is 0,
uh-huh,
and
and G is
1.
that will do it. Okay, so are we all kind of catching this example? Where, in this example here, the second to the last one, if I make E 1, F 0, and G also 1, then 1, 0 in R is true. 0, 1 is in R is also true, but 1, 1 is in R is false. So now finally, we have the left-hand side of the conjunction of the implication being a true, and then the right-hand side being a false, which is the only way you can make an implication to be false. Yes. Yes, because of the universal quantifier. Because the universal quantifier basically says, regardless of how you put values into EFG, we still want the implication to be true. So if you can find me one case, okay, that the expression or the implication is false, then the universally quantified statement is false. Mhm. So are we good with this particular example? Okay, all right. So the last one is pretty easy. This one is definitely just transitive. All right. Shall we move on to the next one?
What would E, F, and G in the previous example?
Huh?
What would E, F, and G in the previous example?
In the previous one,
Is that
E is 1, F is 0, G is 1.
Just to make sure why 1, 1 is always transitive, because we don't have a number to fill in for G, and that would make it false, which is.
You can make E, F, G all ones.
Okay, and that
Yeah,
would.
they can all be the same.
Okay.
But even if they're all the same, this was give you. Mhm. All right, so we doing okay so far with being transitive. So what I'm trying to do here is really just to kind of make sure that we not only understand the properties of a relation, but also to get back to quantified expressions, if and only if, and also implication, because we are basically reusing all of those concepts in the definition of these properties of relations. So you had a question? Yes, go ahead.
So the third example.
Third example being this one. Yes. Yep, go ahead.
So, I'm looking at the 0, 2.
Mhm.
So so that is, is that falsifies true?
Hmm?
For that version, is that why the overall thing is transitive?
Well, there's no one single thing why the relation itself is transitive. It's just that we cannot find a counter example to make the expression false. Or the other way is to say, if you go through the triple loop thing, every single iteration at the innermost loop turns out to be true. So that's the other way to look at it. Is that okay? All right. Shall we move on to the most confusing one? This one is confusing because of the name mostly, okay, but not because of the definition. So now we are moving on to antisymmetric, which is not the same thing as saying asymmetric. In other words, antisymmetric is not the opposite of symmetric. Okay, as much as it sounds like that, that is not the case. So we want to go to this part here, copy, go back to kind of look through all the examples that we have. Okay, so we'll take a look at, oops, this thing here, like so. And then we'll go through all the examples that we have. Okay, so I'm just going to be super lazy here, go through the same 5 examples. And I think it's enough to illustrate, you know, the what makes something antisymmetric. So we'll go ahead and look through every single one of these again, but this time we only want to know whether it is antisymmetric or not. So let me scroll up, make sure this is all visible. So the first one is, if R is an empty set, is it antisymmetric? So how do you think about this? Okay, what do you do in your mind to answer the question? If the default is, did text say anything about this? Then the answer is, well, that may not work in the example. Okay, so you want to go back to the basics. Okay, you want to say, can I find an example here so that the implication is false? But in order for the implication to be false, I need the left-hand side to be true, the right-hand side to be false. Why? Because of the truth table of implication. So now the question is, can I make this part true? Can I make EF in R and FE in R true? Can I find some value for E, some value for F, such that EF is in R is true, FE in R is also true, when R is empty? There's no way, right? Because when R is empty, nothing is in R, which means the element of R thing is guaranteed to return false. So that means the conjunction is guaranteed to be false, which means the left-hand side of the implication is guaranteed to be false. And that means the implication is guaranteed to be true. Okay, so that means the empty relation is antisymmetric. Moving on to the next example. So this one does have some elements, right? But remember, in order for something not to be antisymmetric, we have to find EF in R, FE in R, but E does not equal to F in this case. So this time, I can make the left-hand side true, not a problem. Because if I make E and F both zeros, then EF in R and FE in R would both be true, so the conjunction is true. But guess what? 0 does equal to 0 itself. So I cannot make the right-hand side false. Is that okay? Same thing if they're both 1, 1, you know, E and F are both 1s, E and F are both 2s. So the question is, what if they're different? What if I pick E to be 0 and F to be 1? Then the conjunction is false to begin with. I don't even care about the right-hand side in that case. Is that okay? So in this case, it is also antisymmetric, is antisymmetric. And now into the third one, okay? So the question is this one antisymmetric? Yes. No. If you say no, you have to find me an example, okay? 0, 1, okay, let's find out. 0, 1 is in R, is false to begin with. The conjunction is false.
Sorry.
But yes, the one below that would be you would have been correct. We're looking at the third example right now.
Yeah,
It is antisymmetric. Okay. There we go. Now, onto this one, this is not antisymmetric. It is not antisymmetric because if I make E 0 and F 1, then EF in R is true. FE in R is also true, but E being 0, F being 1, they do not equal to each other. So I found a way to make the left-hand side of the implication true, for the right-hand side of the implication to be false. As a result, the implication itself is false. I only need to find one case like that for the universally quantified expression to be false. Yes.
What would be the
You really want me to say that? I can say that. For all EF in X, EF in R and FE in R implies E and F are the same. That would be the English translation. There's no other way to translate it. Mhm. So you would encounter, okay, in computer science, you would encounter concepts where it does not map to a common word that you use on a daily basis. And antisymmetric is one of those, okay? Yep.
Then why all answers?
That is a good question. I never looked into the why. But I just know that it is called antisymmetric.
I guess it's called antisymmetric because it has to be not the same of E and F. Where like it would be symmetrical if E and F were the same. Therefore.
Go ahead.
So it looks like to me that it's only not antisymmetric if it is symmetric but not reflexive.
That is not entirely true either,
Because
because you can always stick 0, 0, 1, 1, 2, 2 in it, then it is reflexive, right? I know what you're trying to say, okay? You're basically saying it is symmetric, but it has elements other than what makes it reflexive. Yep.
I think I understand why it's called antisymmetric, because it is not. It does not encompass the full scope of what is considered.
Certain cases of symmetric makes this false. Certain cases of a relation that is symmetric will make the same relation not anti-symmetric.
Not antisymmetric means. Symmetric.
Confusing, because it can't R, the first 0, 0, 1, 1, 2, 2 can be both antisymmetric and symmetric.
Well, it is not anti-symmetric because I cannot make this false.
Wait, so R is not?
This part is anti-symmetric.
Isn't it also symmetric?
It is also symmetric.
That's what's confusing.
So it is symmetric and anti-symmetric at the same time. Yes. But it is both. It is really. Okay, I can give you an example. Some people may kind of not like the example. So I can say, okay, look at this thing here. Look at this artifact here. It is a submarine, but it's also anti-submarine. Because it's a submarine, because it is a submarine itself. It can navigate and travel below water, below the surface, right? But it's anti-submarine because it can sink other submarines. So yes, so we can have a submarine that is also anti-submarine. Does that make sense to you? Right? It is not an oxymoron. It is an anti-oxymoron. Yes.
So what I was trying to say is that it seems to me that if it's not, then it has to be anti-symmetric because of, since it's an implication. If it's not symmetric, then the left-hand side has to be false, right?
Okay, so, okay, tell me one more time what you think is guaranteed anti-symmetry.
If it's not symmetric.
Not symmetric.
Right.
Okay, anything else?
No, just that the left-hand side then would have to be false, right?
So you're saying that if it is not symmetric, then it guarantees that it is anti-symmetric or guarantees that it is
Yeah,
not.
guarantees that it's guarantees that it's anti-symmetric.
Okay, so this is what you're saying, right?
Yes.
Okay, so all I have to do to prove you wrong is to find a case, right?
Yeah.
That is symmetric, that is not symmetric, but yet at the same time also not anti-symmetric.
No, that is anti. Okay, yeah, not symmetric and not antisymmetric.
Okay, so let's see if we can find something like that, okay? So we'll go ahead and define R using the same X, because we want to kind of confine our X here. So we want something that is not symmetric. So it's easy to find something that is not symmetric. 0, 1, 0, 2, and 1, 0. That is definitely not symmetric because 0, 2 is missing its quote unquote counterpart of 2, 0. But this is also not antisymmetric because 0, 1 is here. If I make E0, make F1, then EF in R is true. 1, 0 in R is also true, but 0 equals to 1 is false.
Oh, because it's one case, got it, not all
Yep.
cases.
Yep. Okay.
That's kind of what I was saying earlier. That one example, where R is the set of those two tuples, 0, 1, 1, 0, 2, 2, 0. It's not symmetric. Oh, well,
It is not. You mean this one?
I just confused mistake.
Sorry?
I just confused mistake.
Oh, that's okay. I do that all the time. It's okay. So I do have to clarify and make sure the class understands. It is perfectly okay to be confused. In fact, it is a great thing to say, I'm confused, because at least you know that you're confused and not be confused and not know that you're confused. It's always a good thing. Self-diagnostics, okay? That check engine light lighting up is always a good thing, because if that check engine light is blown and it does not light up, and you actually have a check engine condition, that would be worse. Your engine is overheating and you have no way of telling it's overheating until you see steam coming out of the engine compartment. And let's hope you're driving a car with the engine on the front, because if you're driving a rear engine car, you would never see that. Okay, I'm going a little bit too far with the analogy, but you guys get my point. So when you see that you're confused, then what is the next thing when you say, I'm not quite getting this, okay? I got this kind of gnawing feeling that I'm not quite getting it. What do we do? Go back to the definition. Exactly. So go back to the definition and then kind of go, make sure that you understand all the core concepts, okay? All the parts of the definition. Do you understand this part? Do you understand that part? Do you understand this part over here? If there's one part that is screaming and you go like, not getting this part, then you have to kind of go back and make sure you get that part first. Is that okay? Maybe. All right. All right. So let me use this one also as an example because it's a good one. So this one is, okay, I'm going to call all the things. It is not reflexive. That's an easy one. It is not symmetric. That's also an easy one. Not transitive. Not so easy, but we kind of looked at an example sort of like this earlier. So it is not transitive. And it is also not antisymmetric.
So what is it? What is it then?
That's what it is.
It's a relation.
It's a relation that is not reflexive, not symmetric, not transitive, and not antisymmetric. That's what it is, based on all the definitions that we have up to this point. Yes.
Can something be not antisymmetric, but at the same time be symmetric,
Okay, say that one more time. You want something that is not antisymmetric.
but is also symmetric?
Oh, that's easy.
Here.
This one here. This one over here. It is not antisymmetric, but it is symmetric. Okay, I think one way to explain this is kind of like this. If you think about the two tuple, like a person standing in front of a mirror, you can basically ask, do I see a mirror reflection? But the question is that mirror reflection actually myself? The same as myself? Sort of like that. Okay, not quite, not exactly a very good one, but
In that case, after the empty set, that's antisymmetric, reflexive, and symmetric.
Yeah, let's go ahead and complete all of these. Okay, this is antisymmetric. It is reflexive. It is symmetric. It is also transitive. Yep. Any other questions? Okay, yep,
So for a function.
there's no function here. We're only dealing with relations.
Yeah, but like for like a set, is there like a certain set of conditions from the reflexive, symmetric, transitive, and such? In order for a set to be a function?
No, in order to be a function, no, but in order for it to be partially ordered. So in order for a relation to be partially ordering, then it has to be reflexive, antisymmetric, and transitive at the same time. So that's why we have to define all of these conditions, because this is how we can define something that's actually useful to us.
Don't care about if it's symmetric or not. Only those three things.
Yes, this one does not care whether it is symmetric or not. If R is reflexive, antisymmetric, and transitive at the same time, then it is called a partially ordered relation, which means the empty relation is that. The empty relation is partially ordered. Yes.
Covered in the text.
No, the test is only up to and including the G function, mapping the two-dimensional thing into one single dimension. So that would be the last topic included in exam 1, which is next Monday, by the way, next Monday. Yep, just want to make sure.
So Monday coming up.
Yes, yeah. Yep. The 27th. We had to postpone that several times because I forgot that this Monday, the Monday that the past was a holiday. Ready. That's okay. I'm pretty sure the recording is good. Yep. Let me double check on the sound part because yesterday somebody complained and say, yeah, but the sound is not good today.
You said
Swedish
the
is
quiz
working.
was open now, right?
Huh?
So the quiz was open now or no?
The exam 1 is open book and open notes. Same condition as in the practice one.
Okay.
Yep.
You print as many papers as you need, just something digital.
As long as physically it's feasible, bring it here. You cannot go like, well, since I cannot bring all the paper in, I'm gonna park 90% of my material outside of the classroom and only go out. Here.
Patterns are not.
Well, it's not gonna work because just to dig through that much material, it's gonna take way too much time. Yes, if anything, you want to condense, right? You want to condense everything to just what you need. So you can basically go like, okay, there are certain definitions I may not be able to remember exactly. Jot those down. And then you can say, well, those definitions I got it, memorized by heart already. Then you don't have to copy them.
Yeah, anything you know.
Yeah, yeah. The whole concept of study guide is not supposed to be coming from the professor. It's supposed to be coming from each person because only you know what is useful to you. If I were to prepare your study guide, it would be an empty page, right? Because I really know all this stuff. That would not be very helpful to most people. Okay, let me start the recording first. Yeah, go ahead.
Do the notes that we bring in, do they have to be handwritten or does it matter?
No, it does not have to be